Today we will discuss about the boiling. Okay, that is the vaporization of the liquid. Particularly here we will consider the vapor formation of the water, and for that in the different phases the vapor formation or a boiling takes place. Okay, from the liquid state of the water to the its steam state, the whatever the formation of the steam is there, that takes place in the different stages. And whatever these different stages of the steam formation are there, these are called as a regimes of full boiling. Those are called as a regimes of full boiling. Those are called as a either full boiling regimes, okay, under 1 atmospheric pressure. And that whatever the regimes of full boiling is there, that can be explained with a temperature difference versus the heat transfer coefficient or a heat flux curve. Okay, here the whatever this x-axis is there, it is the temperature difference. The temperature difference between the wall and the steam. Okay, that whatever steam formed, its temperature and wall temperature, that temperature difference is given. Here the temperature difference is given in degree Fahrenheit, and here it is in degree Celsius, degree Fahrenheit, and here in degree Celsius we have temperature difference. And in the along the y-axis, ln h, okay, logarithmic term of the heat transfer coefficient we have considered, and that is directly proportional to the that heat flux also. Okay, that's why initially when the heater coil is immersed in the water, this curve is drawn for the heater coil. Electrical heater coil is inserted in a liquid water. Then after that one, the continuous heating will take place, and heat is transferred from the coil to the water, and thereby its water temperature is go on increasing, and when it reaches a saturation temperature, its vaporization takes place. And this vaporization in the distinct zones we are going to discuss here. In that first zone is a free convection. Here initially the heat is transferred by the free convection. Okay, the free convection heat transfer takes place from the coil surface to the its fluid, and its temperature is gone increasing. And after that, next one, it is a nucleate boiling. That nucleate boiling is in two stages, second stage and the third stage. And in the second stage, that is the nucleate boiling of the first phase. That is the most desirable actually, this nucleate boiling. And there the formation of the bubbles on the heater at specific point takes place. Here the vapor bubbles are from the heater surface. The formation of the bubbles will starts on that one, and that in the first phase of the nucleate boiling. And later the rate of formation of the bubbles on at numerous points. Okay, at the number of points the formation of the bubbles will take place, and continuous formation of the vapor bubble, that will be escape from that one, and the continuously the column of the bubbles will be formed from the surface to the that surface of the heater to the surface of the liquid in this nucleate boiling. And this in this one the maximum rate of heat transfer takes place, that is the heat flux is go on increasing, and from this curve we can see that one heat flux is here go on increasing. And at the end of the this nucleate boiling, that is the second stage of the nucleate boiling, that reaches the maximum heat transfer rate. That maximum heat transfer rate, we can say that one critical heat flux or a maximum heat flux, that will be reached. That higher heat flux, this line is a higher heat flux, and that whatever the point is there where it reaches the maximum heat flux, that can be called as a departure from nucleate boiling. And from the nucleate boiling it departs, and it goes for the film boiling later. That's why this DNB point also will call, and also it is called as a burnout point. Behind this one, if you go on increasing, the whatever the heater coil is there, that may burn out. That's why it is called as a burnout point also, and that will give as giving the maximum heat flux, it is called as a critical heat flux point also. Okay, at this point it will reaches the maximum rate of heat transfer, that's a maximum heat flux we are going to attain. And behind this one the nucleate boiling ends and the film boiling starts. And also here the film boiling is divided into the two stages. The fourth and fifth stages are the film boiling only. In that one, the fourth stage is a unstable film boiling. This is a unstable film boiling. Unstable film boiling means the initially whatever the heating is there, the film boiling, the whatever the bubbles forming on the surface of the heater will form a film of the vapor. The film of the vapor will be formed on that one. The continuously formation of the bubble on the surface takes place. This bubble, thin layer of the bubbles will be formed in the form of the film, and that film is unstable. Okay, it forms a film and certainly it will breaks, and thereby the convection heat transfer takes place. Like that, the film is unstable. Okay, then as the film formation takes place, there is a additional resistance of that vapor film will takes place for the heat transfer. That's why heat transfer or heat flux is go on decreasing. Okay, and here the film of the vapor covers the heating element. The heating element, what is there, that will be covered by the this vapor film. And after that one, here this is the unstable film boiling, and when that ends, that will be next will be stable film boiling. In the stable film boiling, the whatever the film will formed, that film is formed the stable on the surface. The continuous film will be formed on the surface of the heater, and thereby again the increase in the resistance of the to the heat transfer, thereby again there is a decrease in the heat transfer. And even though temperature difference is higher, you can see here more than 100 degrees Celsius temperature difference. Not I am telling that when this is a temperature, it is a temperature difference. The temperature difference more than 100 degrees Celsius, there the film boiling will be starts. And here, okay, when nearer to the 1000 degrees Celsius temperature, there the whatever thermal radiation is there, that takes place. Here the convection heat transfer will be ends, and thereby only because of the too high temperature between those two, and also the whatever the vapor is there, that is stable vapor layer will be formed on that one, and thereby the convection thermal radiation heat transfer will be takes place. And that is, even though temperature is too high, the heat transfer rate will be lesser one. That's why here due to the thermal radiation, little increase in the heat flux takes place, but that is not desirable. So much temperature difference we are not going to get from that one. That's why in this one, most desirable zone is the nucleate boiling regime during the boiling of the water. Then here the free convection zone, what I discussed here, the heat transfer takes place by the free convection. In this one, the heat flux whatever is there, that can be given as H into T W into T saturation. Okay, there we are going to use the Nusselt number as a function of the Grashof number and the Prandtl number. And then the nucleate boiling, the two stages already we have discussed, the second and third stage. There the DNV point and critical heat flux also we have discussed. And for this nucleate boiling, whatever the heat transfer is there, okay, the heat flux is there, that is given by this equation. And this equation can be given as a heat flux Q is equal to mu L HFG G into rho L minus rho V by sigma star raised to 0.5 CPL delta T by HFG PRL raised to N 1 by CSF. Mu L is the viscosity, Q is the heat flux, mu L is the viscosity, HFG is the latent heat of the vaporization, G is the acceleration due to gravity, and rho L is density of the water, liquid, density of the vapor, sigma star is the surface tension of the liquid vapor interface, that is depending upon the particular type of the surface. This I will show you, this is available in the data handbook. Okay, for the particular surface. CPL is that is specific heat of the liquid, delta T is the temperature difference between the wall and its steam temperature, and HFG again it is a latent heat of the vaporization that we have taken, and PR Prandtl number of the liquid, N, this N is a constant, it is a 1 for the water and 1 for the water, 1.7 for the all other liquids. And CSF, this is also a constant, CSF is a constant depending upon the heating surface. This is also available in the data handbook that we are going to use for determining the heat flux. Okay, here the maximum heat flux equation, this is also available in the data handbook, and the all other properties, that is mu L, HFG, rho L, rho V, CPL, all these we are going to get for the saturated liquid liquid steam table from the data handbook. Okay, liquid steam table from the data handbook, saturated water and the steam table is available, and from that one we are going to use mu L, rho L, HFG, rho L, rho V, and CPL, PRL, all we are going to get from the data handbook. Okay, that is available directly, those we are going to get, and that is for the its temperature. Okay, that particular temperature we are going to get this TF, film temperature, TW plus TS by 2 for this average temperature of the wall and the steam. That for that average temperature, all other whatever the parameters are there, properties we are going to take. And for the film boiling, the heat transfer coefficient we are going to use this equation, as this is not desirable. Okay, in the many of the cases this will not be considered. And in the radiation zone, if you go, okay, that radiation the heat transfer also takes place, and also the convection heat transfer takes place, and the radiation heat transfer whatever is there, that is determined by this equation. Okay, the radiation heat transfer coefficient we are going to find out, heat transfer coefficient, and then heat transfer coefficient by using that one. Okay, here the convection heat transfer coefficient and radiation heat transfer coefficient, and those mean heat transfer coefficient we are going to determine, and this mean heat transfer coefficient we are going to use in the heat transfer equation for finding the whatever the heat transfer rate is there for this one. And I'll show you data handbook where we are going to use this one. Okay, here this is the equation, heat flux in nucleate boiling. Okay, this equation we are going to use CPL delta T by HFG, PRL raised to N, CSF Q by mu L HFG, GC into G star sigma star, G rho L minus rho V we are going to use, and that is for the maximum heat transfer. If it is that equation is simplified and used like this. Okay, and from this here the properties at the TF 0.5 TW plus of TS by 2 RA 0.5 into TW TS we are going to use, and this is 4 for the force convection we are going to use, and N is 1 for the water, 1.7 for all liquids. Subcooled region this one we are going to use. The CSF we are going to determine for that, and GC is also 1 for water, and CSF here depending upon the surface we are going to determine that one. Water copper surface, it is a 0.013, water scored copper, like that. For the different surfaces CSF we are going to get here, and value of the surface tension that we are going to get here. Okay, for the different saturation temperatures, and for the water and other liquids, this sigma star is given, sigma star into 10 to the minus 3 we are going to get. Like this, all parameters we are going to get from this data handbook, and we have to find the other properties also for the average temperature, and we have to find the whatever the heat flux is there for the particular boiling and regimes of full boiling. Okay, by drawing that graph we have to explain, okay, one by one, that is a free convection and nucleate boiling and that film boiling, radiation. Okay, radiation, like that, step by step we have to explain those in the whatever the happening during that particular stage of the boiling. Okay, thank you, and I will continue with the numericals in the next class.